you can see that the liquid covers the nail, which is what we're looking for. And we now have our final volume measured at 92.9. You subtract the initial from the final, you get a volume of 6.4 milliliters. What does that mean? What does 6.4 milliliters mean? Raise your hand. That's the volume of the nail. So we calculated this volume without doing any math. Now for many of you, that's a good thing, because it would take a long time to mathematically calculate the volume of this nail. Length times width times height. You'd have to bring some geometry in, because you got a curve right here, probably do some calculus. Calculus there with that curve. That would not be easy. So there's a volume you want to take before you take a measurement. We call that the initial volume. So Bowser up here, he's on the far right out of the water. Everybody see Bowser? Where do you see Bowser? Where's Bowser from? Raise your hand. Raise your hand. Lower. Mario Brothers, very good. Anna. So Bowser is going to go into the water, and he goes into the water. How much water is displaced? Raise your hand. 500 milliliters is displaced. So you can see that the volume of Bowser is 500 milliliters. Does that make sense? That's the whole purpose, is to figure out because Bowser has all these weird shapes to it, and to try to measure that, find the volume is very difficult to do. Now how about the toad? What's the toad's volume? Anybody know? Well, let's see. So we have our initial at 500, right? And we're going to put the toad in the water. So how much does toad, what's the volume of the toad? Alright, Christian. 100, very good. So what we're going to do today, we have a little lab over here. We're going to do... That's not how I weigh it. Well, you're going to take it out and weigh it separately.
Huh?
You want to take it out and weigh it separately.
And add it up?
Right.
Hold this.
That's the mass of the ball bearing, right? 7.13. So the mass of this. Now this is a different nail than the other ones. So they have different masses. So they're going to have different volumes too because of the mass difference.
So why'd you do this and this?
Because your density is mass over volume. Makes sense? You take the mass of the nail divided by the volume and you get the density. So you're really talking about two things at once. Talking about the mass and the volume.
So when you did this, did you like... Did you put it on here?
Yeah, mass.
And then you put another nail on there and got that?
Well, like I said, there are 3 different nails.
So should there be 3 different balls?
No, the density should be the same because the volume will be displaced.
So this, like...
Should be the same volume for the nails. Or close to. The density should be the same as the point. The nails, all 3 nails should have the same density. They'll have different masses, different volumes because they're different nails.
So for the ball, like what do you do with this step?
Same thing. You're going to displace the water and then you're going to place it on the balance and measure it.
We did that.
Okay, so what'd you get?
We got the 12
You got 12 for the density of the nail, of the ball?
point something.
Okay, that's good. Write that down.
We did, and then that's it?
Yeah. So if you're gonna do transportation, that's where this comes into play. If you're a truck driver, you can't load the same amount of paper as you do steel, because paper has a different density than steel does, because you could kill people because of this. Paper that you will get, you're gonna place number 1, the object density of the nail. You're gonna need to define it. Like this object here has a C on it for copper. So if you look at the labeling, it'll tell you what it is. So you're going to use these lab write-ups. The difficult part of this lab is I have not given you a lab write-up. So you have to do your entire procedure on your own, which is not easy to do. Now the bell work questions are associated with density. So I'll give you a minute or 2 to answer that. We'll address it. Well, very good. So you can see the submerged copper in there. Excellent. Learning concerns being able to write what you do and think and develop your own data tables. My second period, they were the best class so far. They came up with their own density data table. I didn't have to tell them. That's like super high level learning. You can come up with data tables. You can come up with organization on your own. That's what like employers want you to do without being told. Huh? No, it's not mandatory, but that's what employers want you to be organized. And they want you to be able to do it without being told. When they see that, they'll keep you around even though, you know, you might be new. They find a reason to get rid of the other person before they get rid of you. Well, it's easier to grade. So yeah, you tend up getting a higher grade because it's easier to grade.
Mr. Stein, I just took my water cup. We're just gonna grab
Did I really?
Get off my cheeks. No, straight.
Yeah. Mass, right? Mass, which is right here. And you're going to divide it by the volume when you calculate it from the displacement method.
Okay, what was supposed to be like? Math always. What do we subtract now?
Well, you're going to subtract your final minus initial to get the volume of the substance.
I was looking for the density.
Yeah, so then you're going to take the mass from your balance divided by your volume, like we did for the first one. It was 7.5. Just like watch that all day. Do a lab here on density. Now we're going to do it in this room because students tend to want to drop the metal objects in the sink and then they go into the drain, right? This will fall into the drain like such, and it's difficult to get out of the drain. You got to do the P-trap, so it's just a problem. So what we're going to do today is called the water displacement method. When you have an object like the crucifixion nail, right? That would hurt. It's difficult to measure the volume of this because you've got a curve here, you've got to do some calculus, right? And then you got this difficult object to measure. So we do what's called the water displacement method. And you can see here we have a browser. Now where do you see browser? Raise your hand. Where do you see browser? Oh, Bowser, sorry. Yeah, but where would you see Bowser? Raise your hand. Yeah. Which game?
Mario Brothers.
Mario Brothers, okay. So we have Bowser. It's a fun game. And you can see that when we submerge him, he's out of the water right now. So there's 500 milliliters. Is everybody clear? Then we submerge him. So he's going underwater. So what is his volume? Raise your hand. Yes, his volume is 500 milliliters. Make sense? So the water displaces 500 milliliters. What about the toad?
Well, he's from Mario Brothers as well.
Right? So if we submerge the toad, you see how it's 500 here, right? And as we submerge the toad, it goes to 600, because here's 5, 6, 7, 8, 9, 1,000. You can see that the liquid covers the nail, which is what we're looking for. And we now have our final volume measured at 92.9. You subtract the initial from the final, you get a volume of 6.4 milliliters. What does that mean? What does 6.4 milliliters mean? Raise your hand.
Is that your water displacement?
That's the volume of the nail. So we calculated this volume without doing any math. Now for many of you, that's a good thing, because it would take a long time to mathematically calculate the volume of this nail. Length times width times height. You'd have to bring some geometry in, because you got a curve right here, probably do some calculus. Calculus there with that curve. That would not be easy. Volume and the water displacement minus the initial 6.9 milliliters. So you take the mass from the balance, 51.9495, divided by your volume, gives you your density of 7.5.
The mass and volume.
The water displacement method is to determine the density of the nail. So you need to determine the mass, 51, divided by the volume, 6.4, you get a density of 8.0 grams per milliliter.
That would be.
Your students are also coloring this because these objects tend to make it down the sink, and that becomes a problem. So we do it in the classroom instead. Liters. You're going to place the nail on the side and let it slide in, and it goes to 96.9. So you write 96.9 down. Bell work today, density of oxygen. Now we're going to do a mini lab in here on density using the water displacement method, but while we kind of divide the class, I'm going to have part of the class coloring this, metals, non-metals, and the metalloids. So raise your hand if you know what a metal is. You know what a metal is? Nobody knows what a metal is? What is it? They have certain properties. They conduct electricity, tend to be malleable. But the biggest thing about a metal is they tend to donate electrons. They tend to be electron donors. Okay, so what are nonmetals going to be? Electron receivers, right? Now, this periodic table has the nonmetals associated with the noble gases. They are nonmetals, however, they don't gain or lose electrons. They're considered to be noble. They're nonmetal in the sense that they're not ductile, they're not malleable, right? They're gases, and gases tend to be classified in the nonmetal group like oxygen, chlorine, right? Alright, then what are the metalloids? The ones there in the metal. Metalloids. It's kind of like has both properties. It's kind of like hermaphrodite. You ever heard of hermaphrodite? What's a hermaphrodite? Raise your hand on what hermaphrodite is. Like an earthworm. Earthworms are hermaphrodites. They have both a boy and girl. Reproductive. Now they don't keep both of them on, turned on at the same time. They do that because all earthworms look the same. You can't tell them apart. So they use like a biological clock to mate. So the metalloids have this characteristic where they can be both, both properties, can gain or lose electrons. So color that, color code that. Check the first one. 7.5 is the nail. Make sure you get that density.
Well, that stroke just went by.